Capacitors are the first of our electrical devices that we can put into a circuit. And basically what a capacitor is it's a charge storing device. You've not seen them, but you've experienced them in the flash for your camera. The flash for your camera, you know, the whining that you hear goes nee, and then it winds up and you can hear it, and then it stops, and then the flash is ready. That ending of the whining or the whining is the charging up of the capacitors. And then when you close the shutter, what you're doing is you're allowing the current to flow, and then it triggers the flash on your camera. So the capacitor is actually storing the charge. So basically what a capacitor is it is a set of two plates, and they're attached to some sort of battery, some sort of voltage source here. So here's your voltage. And remember we were talking about the electrical potential between one end of the battery and the other end of the battery. So there's a positive potential on one side of the battery and a negative potential on the other. You've seen the negative and positive terminals on your battery. And so the current wants to flow from the positive, and so we get a positive charge set up on one side of the capacitor. And really what's happening is the electrons are flowing from the negative side, and the electrons are depositing themselves over here. So then the electrons on the other side, on this side over here, are going, they're going back this way. The electrons go in the opposite direction, because remember, everything we're talking about is the flow of positive charge. Thank you, Ben Franklin. But the electrons are going to come this way. They're going to deposit themselves here. They're going to take electrons from this side, because electrons don't like each other, and they're going to repel them. So the electrons are going to get repelled, and that leaves behind a positive charge on one side of the capacitor. And so this is one way that we can store charge in a place. Now the capacitance is basically the ability of a capacitor to store charge. And there's a couple things that come into play when we're talking about a capacitor and its capacitance. All right, the capacitance itself, though, is abbreviated with a big C, not to be confused with charge. But it's a function of the design of the capacitor. So once you've made your capacitor, it has a certain capacitance that does not change. It doesn't change. You can have more charge on it, you can have more voltage on it, but it's not going to change in and of itself. And that is equal to, it's equal to the dielectric constant, which depends. Sometimes you can put a material in between here, okay, and it's called a dielectric, and it helps to make it so it can hold more electrons, because it stops the electrons from jumping that gap. So it's the dielectric constant times E naught, and E naught is a constant, and it has this value of 8.85 times 10 to the minus 12. Okay, so it's a constant, and it's always this number, divided by the distance between the plates times the area of the two plates. So this is areas. This is areas in square meters. So again, you're going to have to make sure you convert your centimeters to meters. This distance is in meters. So you're going to have to, and a lot of times these distances are millimeters, tenths of a millimeter. They're really close together. So you're going to have to convert these to meters. Now, we're not going to use this dielectric constant very often, if at all. The dielectric, basically, you can stick rubber in between these two, but most of the time it's just air, and so when it's air, it's just one. So do you see how that doesn't really affect the equation at all? So mainly we're just looking at this portion of the equation here. Okay? So if I make the area of the plates bigger, it can hold more charge. It has a higher capacitance. And that kind of makes sense, because if it's, if it's little, it can hold a few electrons, but if it's bigger, I can put more electrons all over that guy. So it makes sense that the area would increase the ability to store a charge. Now, the distance, okay, so the distance between the two plates, if you hold those two plates far apart, then you have to build up a huge charge here, and it's kind of like when you are rubbing your feet across the floor, you're building up a charge on your body, and you have to get kind of close to the doorknob before the electrons will jump over. Well, the closer these two plates are, the more the electrons are going to be likely to jump over, because remember, one side's negative and one side's positive, so those electrons want to jump, but if you separate them, the more you separate them, the harder it is for those electrons to jump. So that's what the capacitance is, and it's measured in farads, abbreviated with a capital F. Now, most of the time, these capacitances are on the order of picofarads, which is 10 to the minus 12 farads, or they are nanofarads. Every once in a while, they're microfarads, but a lot of times they're pico and nanofarads. So nano, negative 9, 10 to the minus 9 farads. Okay, so again, we're going to have to standardize our units, but that's basically how we're going to find the capacitance. So this is the capacitance. It is not the charge. We're going to show next on how the capacitance is related to how much charge can be stored. Okay, so now we have a capacitor. Here's our capacitor here. Okay, it's called a parallel plate capacitor because you have two plates, two flat planes that are parallel to each other. And it's applied to a voltage source. So some potential difference here. How much charge you can store up is directly proportional to this voltage source. So the charge is equal to the capacitance times the voltage. Okay? The charge, so this is our coulombs. Our coulombs go here. Our coulombs do not go in for C. Our farads go in for C, and V is our volts, our voltage, or our potential difference. Remember, V is also potential difference. Also, so it's the difference between the two ends of our voltage source. So if I have a bigger voltage, I'm going to have bigger charge. Okay. If I have a bigger capacitor, I can store more charge. So the charge responds to the capacitance and the voltage. The voltage is determined by your source. So whatever your voltage source is, that's what determines your voltage. Your capacitance is determined by the actual design, how you made this capacitor. So if you have a 10 farad or microfarad capacitor, it is always 10 microfarads. It doesn't change. And so what does change is your voltage and then the charge that you are able to build up on the two sides. So from the previous video, we know that the volts are equal to the electric field times the distance between them. Because if you have a parallel plate and you've got a bunch of positives and you've got a bunch of negatives, you're setting up an electric field inside in between the two. Okay, so it's the electric field times the distance in between them. And we know that the energy is equal to the volts times the charge, correct? Because remember, volts are joules per coulomb, so if you multiply that times your coulombs, you get joules. So it turns out that the amount of energy stored in a capacitor equals, it's 1/2 QV. Okay, so that's going to be our energy. So it's kind of an average charge. So 1/2 QV, which once we take all the versions of, Q equals CV and rearrange it, we end up with a whole bunch of different forms of the equation. We also end up with Q squared over 2C, which is our charge squared over 2 times the capacitance. And it's also 1/2 CV squared, or half your capacitance times your voltage squared. But the second two equations, these two equations here, are from rearranging this equation and either plugging in for V or plugging in for Q. So we have really here 3 different ways we can do it. Which way we find the energy is dependent on what we're given. I mean, yes, we can find the missing thing, but this makes our life a little bit easier. One thing to remember though is these equations here, since they've got capacitance in them, only have to do with the energy stored in a capacitor. Okay, so be careful when you use these equations. Don't just stick them in when you've got a point source in an electric field and you're trying to figure out how much energy an electron gains. We're not doing that. We're doing how much energy total is stored in a capacitor. Alrighty, we're going to do this in class, so be ready, and this should be your last video unless you need some videos on some of the pretest questions. Alright ladies, good luck. Bye-bye.